We've got
to fill this up with hydrogen
Also
gas.
colorless.
Okay, it's colorless.
The
Hindenburg was a little
Hindenburg
smaller than this, or bigger.
And we're going to flush
Not
this
much,
out real
not
good.
much.
The important thing
Okay.
is you get this flushed out real good. We like to use a lot of hydrogen.
So you're taking and putting hydrogen gas inside the ostrich-egg is what...
Hydrogen is a potential alternative fuel if we can get it cheaply out of water. It's a great fuel because when you burn it, all you get is water. Fantastic.
And on top of that, it'd be desalinated water too, so you could...
Here we go. I think that should do it. I'm going to
More than enough.
You guys are ready?
We're leaving.
Yes. Let me...
Set this down.
You're standing on my microphone cord.
And you want to light the match, and I'll...
Sure. And you take your finger off the top.
And I'll take my finger off the top here.
Hold, run.
Now, at first, you won't hear anything. But as it burns down, what you will hear happening is perhaps a whining sound, and then maybe a small explosion. Takes a while to get the right ratio of hydrogen to oxygen inside the egg, or hydrogen to air. The oxygen's important. When you get that right stoichiometric ratio, you get an interesting phenomenon happening.
That was beautiful. You're right. I've never seen that before. That is impressive.
Well, we kind of got shell-shocked there.
Yeah.
I kind of like it.
Shell of a mess here. The wall's okay.
This is kind of from the inside. This is kind of... tells us we did all right.
Yeah.
Okay.
Our next guest has just begun his 23rd year teaching chemistry at Napierville North High School in Illinois. Please welcome back to the program, Marek. Lee! Hi, Lee! How are you? Good to have you here. All right. How much time do we have? 4.5. All right, okay. Lee, I'm going to turn it all over to you. Go right ahead. Do whatever you like.
We're going to...
Hit glasses.
All right. In fact, we've got a set for you.
Lens crafter is about an hour.
Okay.
Thank you very much. You folks don't miss a trick. Yes, sir.
I've got an ostrich egg here, and this
of course
didn't
you do,
work
Lee.
last time, but I've got it perfected
Oh, that's right.
this time.
You fill it full of hydrogen, then it explodes or something. Is that
You
right?
got it. Last time we used the goose egg, and that didn't work too well, so this time we're going to go upscale a little bit.
These are all things you do in the classroom there in Napierville North High School in front of the kids.
We give it our best shot here.
Ever set fire to a kid's hair?
No, not lately. That's not a bad idea.
All right, you're gassing up your egg.
Yeah.
Why don't you folks at home do the same now while you're It'd be an excellent opportunity to gas up the egg.
Now, I'm going to light this sucker. We're going to close that door.
Wow, wow, look out. Run for your lives.
All right, now you may want to cup your ears.
Uh-huh.
And as, I bet you can hear me well, as that burns down, air starts to enter the bottom. And pretty soon you'll get the right ratio of air to hydrogen inside there, and you'll get an effect something like what happened with the Hindenburg. I'm sure you'll find it interesting. Well, we'll see what happens. It makes a great fuel, by the way, because when hydrogen burns...
So you get yourself a room full of kids who can't hear for the rest of the semester.
Okay, this...
Mr. Marek! Mr. Marek!
Jeez, look what we found laying here.
Boy, I bet the chicken got a hernia doing that. No,
Wow.
that's an ostrich egg, Bob.
That sure is.
Look
And
at that
it's
hole in the bottom.
got a hole in the bottom.
There's a little hole in the top. Gee, you know, we could probably fill that with hydrogen gas. It would be...
Exciting.
Certainly would. We'd have to make a quick...
Exit.
No doubt about it. Luckily, we're not exhausted, so we can do this. And we shouldn't think too much about it and get it real existential. So, we're going to fill this up now with hydrogen. You're going to hold your hand over that?
I'm going to try.
You're going to try. Okay. Pull this in just a tad.
Do you suppose we could suffer shell shock from this?
I don't know. We could try it. See if we get the old shell game going here. Sounds like... Okay, I'm going to put the splash shield in front just in case.
There might be an egg explosion.
That's right. We hate to get anybody's brains scrambled up, but that's all right. You're a pretty hard-boiled guy, so I'm going to leave you here. I hope you don't poach yourself. You want me to light this for you and
Okay.
hand it to you? And then I'll make that quick exit that you talked about. Hey, good luck. Far not much is happening. These are pretty hard-shelled individuals. Oh no! Oh no!
The sweat.
Somebody shot him in the side of the head.
Where's the other one? The other one do anything? Oh, I feel all white. Oh no!
I've got a splitting headache.
Oh no! The other one. Oh!
Uh-oh.
Better stop it now.
Better stop it. The nose
the
on
nose is going. I didn't even poke that. It is going there. Oh, this could be good. Oh, it's crying. Oh no, I feel sad.
Got a cold? Got a cold, buddy?
This is not funny at all.
It's real nasty cold.
No wonder they call it mucous membrane.
Oh,
Oh no! Keep an eye out for me.
The other one on the other side, he's so tough.
My pupils will love it.
Just get over and get the other one now, Dave.
Well, that was a good one. I like that one. Oh, that looks disgusting. Oh, the other one's cracking. It's cracking. Oh, I love it. Oh. Oh. Talk about a split personality. Oh! Went good.
that was the bottom one.
Sarah fell on Mary.
One at the back.
The one's oozing out the back and the bottom. Not, oh no, help me.
Dumped a lot out.
Yeah, the other one, I don't know what's happening to it.
The bottom again.
Oh. Not impressed with those chocolate ones.
There he goes.
It is sort of melt.
Meltdown.
Nuclear meltdown.
Well, it's really disgusting. Ooh, it's growing massy. Look at that. That is really.
Just show this tape to your classes for years?
Yes. Experience, Dave. Here today, gone tomorrow. Oh no! I don't know if I cared for this. Oh no! Oh no! Oh, I feel swell! Help me! I'm melting! Oh no! Oh no! The other one's still oozing out the back. Oh no! My friends! That's cute.
Now they're really starting to expand. And one's smiling all the way down.
Oh no, help me! I feel swell. Charles' Law. As the temperature goes up, the volume goes up.
Somebody made for you.
Look at the oven. Oh God. The eggs come next.
Send Scott down to get me when you're ready for the eggs.
All right. Well, we'll do a trial one first.
Okay, and then send down to get me.
Yeah,
We
that's.
might not have an oven after the trial one.
We're just boiling here now.
All right, we'll kill it, Dave.
While reading a textbook of chemistry, I came upon the statement, nitric acid acts upon copper. I was getting tired of reading such absurd stuff, and I determined to see what this meant. Copper was more or less familiar to me, for copper cents were then in use. I'd seen a bottle marked nitric acid on a table in the doctor's office where I was then doing time. I did not know its peculiarities, but I was getting on and likely to learn. A spirit of adventure was upon me. Having nitric acid and copper, I had only to learn what the words act upon meant. Then the statement, nitric acid acts upon copper, would be something more than mere words. All was still. In the interest of knowledge, I was even willing to sacrifice one of the few copper cents then in my possession. I put one of them on the table, opened the bottle marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. But what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. A greenish-blue liquid foamed and fumed over the scent and over the table. The air in the neighborhood of the performance became colored dark red. A great colored cloud arose. This was disagreeable and suffocating. How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out of the window, which I had meanwhile opened. I learned another fact. Nitric acid not only acts upon copper, but it acts upon fingers. The pain led to another unpremeditated experiment. I drew my fingers across my trousers, and another fact was discovered. Nitric acid acts upon trousers. Now, taking everything into consideration, that was the most impressive experiment, and relatively, probably the most costly experiment I have ever performed. It resulted in a desire on my part to learn more about that remarkable kind of action. Plainly, the only way to learn about it was to see its results, to experiment, to work in a laboratory.
And we're going to do some very amusing. What is density? Well, let's take a glass of water and weigh it on a scale. Now, let's weigh a glass of salad oil. Picks up the same amount of space. The reason the oil weighs less than water is that the particles that make it up are not packed so tightly together. We say the oil is less dense or has less density. If a solid or a liquid is less dense than another, it will float on top of it. Knowing that is a sensational trick. You can make steel appear to float on milk. How do you do it? Well, just get an egg cup and pour some mercury into it. You can get mercury from any large chemical supply company. Then cover the top of the mercury with a little milk. Just enough to hide it. Drop a steel ball into the milk. And the steel will appear to float on milk. Actually, the steel is floating on the mercury. The reason it floats on mercury is that steel is less dense than mercury. But steel is more dense than water. If you put it into water, it sinks. You can do a very unusual demonstration because any material will float on a liquid that is more dense and sink in a liquid that is less dense than it is. First, pour some mercury into the bottom of a tall glass and float a steel nut on top of it. Now pour in some carbon tetrachloride cleaning fluid. If you don't have any mercury, start with the carbon tetrachloride. Float a plastic bottle cap on the carbon tetrachloride. Now pour in some water. And float a block of wood on the water. Now add a layer of salad oil. And float a cork on the oil. Each of the liquids is less dense than the one below it, so it floats on it. Each of the solids is less dense than the liquid on which it is floating, but more dense than the liquid directly above it. So it stays where it is, giving you an unusual demonstration of density. Now, it's not only different materials that have different densities. The same material may, under different conditions, have a different density. Cold water and hot water have different densities. Which of the two do you think is more dense? Cold water or hot? Well, here's an experiment you can do to find out. First, pour a little ink into a small vial. Then fill the vial with hot water. And set it into a container of cold water. The hot, inky water rises to the surface of the cold water and floats on it, showing that hot water is less dense than cold water. As the ink cools, it becomes more dense and slowly sinks. Here's an experiment you can do that will show you something else about density. Take a small light bulb, put the bulb in hot water, and it floats. Now, wind wire around the neck of the bulb until the bulb just sinks. Now get some ice-cold water and add it to the hot water. As the hot water cools, it becomes more dense. Soon, it is more dense than the weighted light bulb, and the bulb rises to the surface and floats. So you see that you can make an object float on a liquid by making the liquid more dense. And knowing that, there's a puzzle that you can show your friends. Fill a glass with water and drop an egg into it. The egg is more dense than the water, so it sinks. Now challenge a friend to make the egg float without touching either the egg or the glass. When he gives up, you show him. Just get some salt and pour it into the water. Salt water is more dense than the egg, so the egg rises and floats. And now let's get closer to understanding this instrument, which a gas station attendant uses to test the liquid in a battery. Put a thumbtack on one end of a pencil and drop the pencil into a glass of water. Make a mark on the pencil where the water line comes. Now, once you know how deep the pencil sinks in water, you can use the pencil to test the density of any liquid as compared with water. For example, if you put the pencil into salt water, which is more dense than water, it floats higher. If you put the pencil into salad oil, which is less dense than water, the pencil sinks deeper. Now, the density of any liquid, as compared with the density of water, is called specific gravity. Shows specific gravity of liquids, their density as compared with that of water. Hydrometer. If you put a hydrometer into water, it sinks to the figure 1. If you put it into salt water, it indicates a higher figure. Because salt water is more dense than ordinary water. The battery in an automobile has an acid solution in it, sulfuric acid. When the battery is in good condition, the solution is dense, and the hydrometer floats high. But when the battery has been used too long and must be charged again, the solution is weak, less dense, and the hydrometer sinks low. So, by measuring, the hydrometer tells us the condition of the battery in an automobile. And now you know a great deal about density and have many interesting experiments to try.
Accidental explosions give no warning. They can bring death or lifetime injury. Each laboratory worker knows the need for safety shielding in chemical laboratories. We firmly believe that the academic laboratory can be one of the safest places in which to work with the proper shielding devices. Implosions of low-pressure equipment, such as Dewar flasks, spell possible danger. Here, too, the chemist must have special shielding to protect himself. Many accidental gas explosions in academic laboratories have been mixtures of hydrogen and oxygen. For experimental purposes, the explosions can be sharply triggered. The explosion range is very wide, but for our experiments, the proportion of hydrogen and oxygen in water was used. The gases are easily measured by water displacement. The slow motion picture shows more clearly the violence of the hydrogen-oxygen explosion. In this case, all movable objects were swept away except the wash bottle. The shattered ignition assembly dropped back from the ceiling, while the eudiometer slowly fell away from the explosion center. Any seasoned teacher can recall many case histories, some tragic, some fantastic escapes. This case history is a typical part of a hydrogen experiment. The nearest freshman removed her safety glasses. Apparently, her apparatus had not been checked or the generation of pure hydrogen verified before she lit the burner. She suffered the loss of one eye. The other two students were not hit by the widely scattered missiles. In this case, the student added sodium shavings to vanadium oxytrichloride. The inside surfaces of the hood were covered with corrosive liquid and bits of burning sodium. The student was not hit. In case history number 3, magnesium perchlorate was used in the organic preparation on the left. Both students were wearing substandard safety glasses. The student on the right was not hit, but the explosion on the left demolished that apparatus and destroyed one eye of that student. The research chemist in case 4 used a steel spatula in transferring his perchlorate preparation into a wide-mouth storage bottle. He had not provided any kind of shielding. The violent explosion badly mangled his left hand and caused fatal internal injuries. He never regained consciousness and died the second day. To better understand the erratic nature of laboratory explosions and some fantastic escapes from glass missiles and splashes of corrosive liquids, a plan was instituted for charting the explosions. The charting paper was sensitized. After each explosion, the torn parts of a chart were assembled on the table and repaired where necessary with transparent tape. The chart was then attached to an easel. Holes are easily detected against a dark background. In all the charting experiments, no two identical charts were ever discovered. The distribution of missile hits and splashes appear to be totally unpredictable. Color depended on combination of solutions used. To make this study more realistic, the chart was replaced by sensitized papier-mâché masks equipped with eye and face shields. The explosion flask was centrally located as before, and a suspended body shield was placed across the opening. The erratic nature of the explosion was quite evident by the wide difference in impact of splashes and glass missiles. The left lens of a safety glass was shattered, but was not blown loose. 8 selected masks with shields removed show the difference in protection by comparison with number 0 mask, which had no shield. Safety glasses on 1, 2, and 3 allowed some spray to reach the eyes. Goggles 4 and 5 offered surer protection. The face shield on mask 6 had a short window, thus exposing the lower part of the face and the neck. The penetration of the neck by a large piece of glass should convince us that an adequate face shield should cover the entire face, scalp, and neck. The shield on 7 had an 8-inch window. The wide coverage on number 8 displayed the most desirable protection. We turned 8 masks with the same shields through 90 degrees to show the protection offered from the side. The side attack from the explosion resulted in some spray reaching the exposed eye of number 1 and of number 2. The solid side shield on number 3 stopped the spray. Of the goggles, the one on number 4 with perforated sides allowed some spray to pass. The solid sides of goggles on number 5 stopped the spray. The narrow windows of the face shields on number 6 and 7 exposed the ear canals, while the very wide window on number 8 offered full protection. Our selection of eye shields must be primarily for protection of the eyes. Many devices are on the market, ranging all the way from some lightweight visitor's glasses to the standard safety glasses and the more protective goggles. Safety glasses may be plain or supplied with perforated or solid side shields. Goggles are typical designs. The ease of wearing goggles consistently depends very much on proper fitting. This student is adjusting the elastic band just firmly enough to gently hold the goggles in place. Our selection of a face shield depends on the type of work to be done. Some leave much to be desired for coverage of the whole face. This student has chosen a sturdy shield with easy adjustments for height and circumference. By proper adjustments, he has made it as comfortable as his old hat. We will cite but one case history of an implosion accident. A biochemist was fatally injured when his suction filtration flask imploded. This slow-motion picture shows in detail one imploding suction filtration flask. Implosion of a Dewar flask can be dangerous as the sharp, heavy fragments move away from the implosion center. In this case, the graduated cylinder, the wash bottle, as well as the mannequin face were pelted by the large fragments of glass. Watch the red stopper. A Dewar wrapped with electrician's tape is a safer flask. Shattered walls were quite well contained. To carry on a chemical operation without sufficient shielding of the body as well as the face can be very dangerous indeed. The chances of complete escape from injury are quite remote. The eyes, face, and neck are vulnerable. Heavy glass missiles can cut through ordinary clothing. Shield A has a laminated glass window and a light metal base. In slow motion, this same event shows more clearly the violence of the number 4 charge explosion. The flask was completely demolished. The liquid and shattered glass were hurled against the shield with such force that it was tipped beyond the point of balance. This poorly balanced body shield struck the face shield and scratched the window as the mannequin was struck down. The face shield prevented a severe blow to the forehead and nose of the mannequin. The impact would have registered severe bodily injury to a live subject, especially if only safety glasses had been worn. 4 kilograms are added to the heels of Shield A. The stability was greatly increased, as shown by this slow-motion picture. This study could be extended to include variations and positioning of added weights. Added weight increased the stability of Shield A, but the unprotected window on the left withstood but one blast. This display shows in the center a Lexan sheet which protected the laminated glass on the right during 6 explosions. This 1/4-inch plexiglass shield, mounted in a heavy lead base, is a stable shield to begin with, but can be made even more stable with added weights. This custom-built shield, suspended from a track on the ceiling or from rods, occupies practically no workspace and has the advantage of swinging out at the bottom. It cannot tip. What are the requirements of a good safety shield? This visitor's glass was described as light and comfortable. One lens was blown out and the other cracked. Here we show only the results of the explosion. This pair of much heavier visitor's glasses with solid side shield offered good protection for the eyes. This visor-type goggles withstood a mild explosion remarkably well. It can be worn over prescription glasses very comfortably. This substandard 20,000th inch window on a face shield for general purpose is inviting tragedy. This demonstration should convince us that only the minimum standard 40,000th inch window should be considered. This comfortable, very long and very wide shield with thickness in excess of the minimum standard withstood the same number 3 charge explosion. We can hope that these specifications are accepted as the minimum. Potential danger lies in all laboratory explosions and implosions. We firmly believe that with proper shielding at all times, the chemical laboratory can be made one of the safest places in which to work. Much safer than the home, and far safer than our highways.
Presenting the Supermole Shuffle. Written by Naperville North's Matt Patterson and Dave Wang. Performed by Dunwoody's AP Chemistry students.
One, two, three, go.
We are the Chem Shuffling Crew, doing all that, doing it for you. We're so bad, you know we could, blowing up labs like you knew we would. You know that Chem's just for fun, counting those rolls for everyone. We're not here to start no trouble, we're just here to do the Super Bowl Shuffle.
My name's Avogadro, I'm a gas. Some thought my theory just wouldn't last. My heart was safe to assume, same no particles, same volume. Made the mold to stand again. The students attest, they just can't do it. I'm not here to start no gas. I'm just here to count the more mass.
I'm diatonic. What's my name? You guessed me right, you love this game. But hold on now, don't guess too soon. At STP, I'll fill the whole room. Another clue. Unless you know, when I'm on your teeth, they'll start to glow. One last clue, not hard to miss. When I'm a comfort, it's safe to kiss. If you're smart, your teeth are clean. An accurate guess would be blurry. I'm not here looking for trouble. I'm just here to do the Super Bowl Shuffle.
It's hydrogen here, I'm all alone, no chemical family to call a home. I span the length of the periodic table, I'm a real cool cat, never unstable, but when a lot of me fused together, we make the elements that are heavier. More reacts than you will find, none of the elements will be left behind. I made lithium, radium, uranium too, but the carbon I make is just for you. I'm not here to cause no trouble, I'm just here to do the Super Bowl Shuffle. Words.
It's carbon here, and I'm the main man. When I combine, I've got a big plan. I need for more to be inert, and hydrogen and I just love to flirt. I make up your head, your torso, and feet, and when I'm under pressure, hey, don't look neat. I'm not here to start no trouble. I'm just here to do the Super Bowl Shuffle. It's silicon now, I'm found in sand. If carbon can't combine, then hydro can. There are other life forms based on me, but if you saw him, you'd probably flee. Don't get me wrong, I'm a real nice guy, and when I'm in computers, the work really flies. I'm hard to find, except on the beat. Another life form I can't read. Don't be thinking I've got some trouble. I'm just here to the Super Bowl shop.
It's Kelvin here, and I'm no fool. 273 is really cool. Me and Celsius are nearly kin. A fine line between us that's really thin. Foolish chem students think I'm dirt, cause in their problems they forget to convert. That's why you're here, to see me on the double, to catch me doing the Super Bowl shuffle.
235, down to a name at the British nucleus, McLean the fame. But some of the products cost a bit hard. Some we got better sun the year long. Some have half-lives that are really long. Those are the ones that make nuclei wrong. I didn't come here to cause no trouble. I just came to do the Super Bowl shuffle. 1, 2, and go.
We are the camp shuffling crew, doing all that, doing it for you. We're so bad, you know we're good, blowing up labs like you knew we would. You know that camp's just for fun, counting those wolves for everyone. We're not here, starting no trouble.
Full Shuffle, starring as Avogadro, Scott Jackie Baby Jackson. As Fluorine, print hip-hop all spots. Hydrogen, Scott Too Fresh for You, Osmond. As Carbon, Scott Kick Beat. Silicon, Amir, Bob the Terrorist Abbas. Kelvin, Danny Rhythm Di Pasquale. As U235, Dave, Mr. Tempo Sweet. In the Peanut Gallery, we have Mark Somerville, Travis McLeod, Steve Reynolds, Brett Mutnick, Tom Meehan, Kirsten Miller, and Grace Rue with the Mother Mole and the Little Molars. Behind the scenes, Lynn Fancher, Adam Culbers, Denise Nickerson, Jason Domzel, and Leslie Haynes. This has been a Broadway Molar production.
Rolling.
Okay, I've got a pencil here. This is a pencil rifle. It shoots a pencil 300 miles an hour through this tube. Sure it does. I'm going to hook up this CO2 extinguisher to this. Okay, and Tim, if you would pan down this way so you can see how long it is. Great. Got a block of wood here, like this, that I put in here. Here's the end of the pencil gun. Let me seal it up just for safety's sake.
Sarah, you here?
Okay, shut it off, Tim. And then we'll ready to shoot now. What you're looking at is the wood in a plexiglass case. And we're going to shoot the pencil right about now. I just have to karate chop the fire extinguisher. 1, 2, 3.
Holy crap. Oh my gosh.
That's nice.
That is all right, isn't it? You can see it going right through the piece of wood. It's rolling. All right. Phase 2, this time I have an unsharpened pencil, and this is fairly interesting because this one, in theory, goes right through the wood. It's an inertia problem. 1, 2, 3.
Nice.
Wow.
That's nice.
I'll go get him. It's kamikaze. Come over here. It's going better.
He's gonna shoot it right through Charles. That's unreal.
Suicide troll.
Very sharp pencil.
Get this level up. Gotta give it some wax too. Gotta give it a wax it if you.
All right. You ready now? Okay, this time we're going to do it with an unsharpened pencil. One, 2, 3.
Oh, yeah, that one's stuck.
Where's the pencil?
Yeah, where's the pencil?
It's right.
Right.
Nice. Where's
The pencil? I don't know. It's gone somewhere in Lyle. Here we go. 1, 2, 3. Yep.
Yeah. That's a good job on them that way.
And Eureka! Yes. Bring on the kids.
We have to qualify this a little bit. Lee teaches mostly AP now, and I teach almost all general.
Well, this water's warm. He may.
He may, yes, he may. But so we had to go searching through my class until we really found a really dense kid. I think we have the perfect student. If you could really, this is his first time in something like this in a public performance, so please make him feel welcome. Give him a big round of applause.
All right.
Yeah, it's made an old campsite.
That water's too warm. We've got some calibrated devices here. That you can get this Vizimo lens, the best use they can think of it. It's right here. And, Bill, you put too much in. Where did it go? Is that okay? I'm not having to go in there all dry ice. Who's second? We'll let this cook down a while. And we'll kind of put them in.
So what do you want to go to next person?
Yeah, we'll go on to the next person. Then, I much prefer to be in pounds, and the kids would have to do the calculation. Okay, take your shoes off. All right. Get out there. Now, you people are going to write down these measurements, aren't you? What is it? That's enough.
No extra charge.
What do you got there, kiddo? 60 kilograms. That's 60.0 for you Sig Fig freaks and physics teacher. All right. Now, got the buckets here, Mr. Grosso. We have the buckets. We have the buckets. All right, in you go, kiddo. Water's warm, don't add to it. Where's your girlfriend? Come on down, you gotta help, you gotta hold the hose here. Yeah, here. He's gotta breathe when he's underwater. Right. John's going to be getting set up. We'll take the volume measurements while John is doing his thing. Hey, brother. That second one ready here. We're going to do a woman too, but she chickened out here. Okay, go quick. I did. I had a girl that really wanted to do this. Try to hit the containers. Experimental error. Story of your life.
He does have a bucket of water.
Been that way ever since he was a little kid.
I blame it on my 3-year-old at home.
Maybe he needs to walk to bed.
Yeah. Well, he was gifted, I know. All right.
Now who's that chemistry with the song?
That is. Yes, in case you're wondering, it is extra credit.
The really good part is that when he was changing, he dropped all his real clothes in the toilet, so.
Promised him he wouldn't tell. All right, look at that. We're going to make it. All right, we grasp the concept. You ready? You ready, John? John? All right. Anytime you're ready to go on, we'll just continue taking the volume.
Okay, this is John Brodemus from Richards with Michael Baccarat from Friend on deck. And I'm going to have Rich Hall help me out. 3 quickies. Some of you people like to have things on Marlite boards where you can have the dry.
9.3. So we'll let you calculate it. That's liters, we believe. 59.3 liters.
Know that I do 3 types of chemical demonstrations. They involve either radioactivity, toxic materials, or explosives. And that's not entirely true. Tonight's category is number 3. One of the materials that we rarely get to work with are the perchlorics, which seem to instill just a bit of fear in you when you even write the word down. The actual parent material is perchloric acid. This was actually discovered in 1816 in Germany by a very daring chemist who didn't have the faintest idea what he was doing. He had a solution of potassium chlorate, concentrated solution of potassium chlorate, added concentrated sulfuric acid to this, heated it, and distilled the azeotropic mixture, which turns out to be a solution of 72% for perchloric acid, which is the concentration of the concentrate material if you were to purchase that in a bottle. This is approximately 12 molar. Now, if you proceed a little farther with that reaction, if you heat the 72% perchloric acid, it starts to dehydrate, and it eventually ends up as a monohydrate solid, which is violently explosive. Now, most of the factories that produce perchloric acid have long since disappeared. In fact, there are very few facilities that even still make the material. Well, the chemistry is a bit hindered on this because virtually every experiment you do with it almost ends in a disaster. The perchlorate ion, however, does combine with a number of cations, both organic and inorganic, to make very beautiful crystals. So it is often used as a material to isolate materials in a crystalline state. Now, it took until almost 1900 before they actually discovered the anhydride of this acid, which is Cl2O7. Okay? Now, you probably know that the oxidation state of the chlorine here is +7, which makes this a very powerful oxidizing agent. In fact, perchloric acid and many of the inorganic perchlorates react virtually explosively with any type of organic material. Okay, now we can look at some derivatives of this material. Now, there are a number of sols and perchlorates, and the one that I would like to look at in particular is ammonium perchlorate, which can be made from just a simple neutralization of ammonia with perchloric acid, but it's usually not made that way. Most of the perchlorates are made by an electrolysis procedure. Now, starting with the chlorate, so this accidental synthesis here was actually very important. Starting with that, you can electrolyze it or use an oxidizing acid to produce that. Now, ammonium perchlorate was sort of made as a novelty item until about 1900. But then World War I and World War II produced a significant demand for this material because of its explosive character. And toward the end of World War II, this material actually experienced a significant surge in production because then it was used as an oxidant as rocket fuel. Now, it is actually still made in tremendous quantity because ammonium perchlorate reacting with aluminum is actually the fuel mixture for the Space Shuttle solid rocket booster. So when you see the Space Shuttle launching and there's that immense white cloud, it is actually the aluminum oxide formed in this reaction. So for those of you who like to do these little homemade things, it's about 70% by mass ammonium perchlorate and approximately 16% by mass aluminum. Now that doesn't add up to the whole amount. Why? Well, when you prepare things like rockets, you have to control the burn rate. It's very important to have proper burning. So the remainder of this is actually a plastic material used as a binder to maintain the physical stability of the fuel mixture. It burns evenly going up. Now, actually to this we add a little bit of a catalyst, a little bit of iron-3 oxide, a trace of that. Some of you may notice that this is looking strikingly like the ingredients in the thermite reaction, which it is. Okay? But in that case, it's aluminum reacting with a significant amount of this, so we're going to use only a catalytic amount of the iron oxide. And I will not be synthesizing the binder in this. Ammonium perchlorate is actually not a very stable material. This is made in... Ammonium perchlorate is made in Hendersonville or someplace in Nevada. 1988. That is the supply place, by the way. It makes all the ammonium perchlorate for the shuttle rockets. 1988, the plant blew up. It's several miles out of town. It leveled almost half of Hendersonville, which is a few miles away. It just literally decimated the town. Blew up 50% of the buildings in the town. And that actually slowed down our shuttle launches because we lost our whole supply of ammonium perchlorate when that went out. They store it outside in 55-gallon drums. They space them out now a little more than they used to. We learned from and then aluminum. I never mix these until right before I use them because sometimes they decide to ignite just in the mixing process. So, you know, there's really no point in doing a demonstration unless it involves a little danger, right? But okay, aluminum and ammonium perchlorate. And I'm going to intentionally use rather small amounts because this is coating. So I thought I would show you this because most people don't want to do this in the classroom or fear of losing your students. Of course, every good chemist carries these things around. For those of you into reaction temperatures, this reaction proceeds at approximately 5,000 degrees Kelvin. Okay? Needless to say, I will not be standing here. This is the iron oxide catalytic amount. Now it takes a significant amount of heat to start this, and I'm going to insert a magnesium fuse. Into the center. You know, in all the shuttle launches, I've never seen a picture of the guy that lights it. In a moment, you'll know why. Now that reaction is taking place in an iron crucible which is melting right now. The smoke, aluminum oxide. That's the iron crucible now. It's still at 2,000 centigrade. Now this, actually I did this to give you an idea of why you think the O-rings may have failed on the joints between the sections of the Challenger. Okay. High temperature reaction, and it takes a pretty significant amount of high temperature material to withstand that. So it's not your typical reaction for you to take home. Thank you.
A submarine in trouble at 1,000 feet. Options for escape are minimal. At that depth, pressure on the lungs holds gases in the bloodstream like bottled soda. Quickly surfacing would release the pressure and bubble the blood. This could be a solution. Breathing liquid. Fluid-filled lungs would resist pressure change.
You could go as deep as you wanted and stay as long as you wanted and come up as fast as you wanted. You could come up from 1,000 feet as fast as you could go.
We all breathe liquid for 9 months, Bud. Your body will remember.
While this is done by special effects here, its potential is real, and made practical by perfluorochemicals. Such chemicals hold more life gases than air and are so biologically safe they can replace blood.
Right.
They fill the delicate interior of the lungs without irritation. Breathing them could even be therapeutic for damaged or diseased lungs. A premature baby recently became the first human to actually rely on liquid to breathe and demonstrated the potential of using perfluorochemicals to prolong womb-like conditions in underdeveloped lungs.
By putting a fluid in the lung rather than a gas, it's much easier to expand these lungs at lower pressure and therefore is less likely to damage the lungs of these infants.
A similar technique could protect astronauts from the massive acceleration forces expected of future launch methods.
The liquid-breathing astronauts suspended in a womb-like capsule could easily tolerate, at least for a few seconds, such accelerations.
Liquid breathing's potential continues to be explored in areas as diverse as imaging techniques and endangered species breeding. I'm Randy Atkins for the American Chemical Society. A police surveillance camera provides graphic evidence of the drug war's urgency. Suspected drug deals side by side with children's play. New generations potentially being steered toward a dangerous path that police have trouble blocking. A path largely being blazed by smokable cocaine, crack.
Although crack is simply one form of cocaine, it has certain inherent problems that make it more dangerous.
What's been really dramatic for us is to see how quickly patients become compulsively involved if they smoke the drug. You snorted for a while before you started smoking it. When you started smoking it, how quickly did things get out of control?
Quickly. That was a big change. It was a drastic change. It was devastating.
Has to do with the subjective effects when you get cocaine to the brain very quickly. And when you smoke it, it gets to the brain in only 7 or 8 seconds.
At least as fast a delivery method as the injection these mice are getting. This image of a human brain after radioactive cocaine injection shows that the drug completes its path by binding to very specific brain sites. Sites that trigger reactions ranging from the high these mice probably feel to this, to this.
The difference between a dose that will produce stimulation and a dose that will produce convulsions is very small.
So scientists are desperately trying to block cocaine's final steps toward those brain sites, waging the drug war's final combat within a complex biochemical battleground.
Ultimately, if one understands the neurochemistry behind cocaine binding, then maybe one can design some sort of a specific therapeutic intervention for cocaine abusers.
Chemical warfare at the ultimate border. I'm Randy Atkins for the American Chemical Society. Despite the tubes, needles, and wires, this longtime drug user can hardly wait for what's about to happen. For as scientists probe, this syringe will be sending cocaine to his brain about as quickly as if he'd smoked crack. And to him, that means
A joy that has just got you wired up tighter than a 9-day clock. It's good.
the brief but intense artificial bliss.
Excellent.
That's at the root of perhaps America's most pressing problem. The reason so many find it so hard to say no.
It's very easy for us to say this is a question of morality, just say no, but people who are already hooked on cocaine are not going to be easily gotten off of it.
If we understood craving, if we understood where in the brain craving was localized, we could identify chemical systems that are altered in craving and develop medications to help alleviate craving.
But first, scientists must understand what's being craved, must understand the biochemistry of that cocaine high. And positron emission tomography, PET scanning, is revealing it with frightening clarity.
A PET scan is unique in that it can probe the biochemistry of the brain. It can probe how chemicals interact in the brain.
This PET scan shows normal activity in the brain's most highly developed region. This, the same region, just minutes after a cocaine injection.
The metabolic rate in the brain is close to what you see in an Alzheimer's patient. The brain is almost non-functional metabolically.
But ironically, that deadened brain unleashes a dangerous flurry of activity throughout the rest of the body. Activity that can quickly lead to permanent damage or death. I'm Randy Atkins for the American Chemical Society.
Whether I had money or not, the thought of using the drug is overpowering.
Cocaine dependency described by a former crack abuser.
It interferes with every aspect of your life.
And the reason is becoming very clear as scientists use positron emission tomography to chemically trace cocaine's path.
One can tell exactly where cocaine binds in the brain, how long it stays in the brain, how rapidly it clears.
Its main target is the area of the brain that produces the pleasure that encourages actions necessary to human survival, like eating and sex. Cells there communicate through a chemical signaler called dopamine, represented by green circles here.
In any mode of communication, there has to be a discrete signal. So dopamine has to be released, and then its action has to be terminated. And cocaine interferes with the termination of action of dopamine.
Most scientists now believe cocaine does that by binding to a site responsible for the reuptake of dopamine, blocking its passage. As dopamine accumulates between cells, signaling increases out of control, producing an artificial reward that bypassed any benefits.
Essentially, you've tricked the brain into thinking that this behavior, the drug getting and the drug using, because it produces this powerful, intense reward, is the most important thing in the world to do.
When the drug is all going, then I get a feeling of emptiness.
A feeling only satisfied by a dangerous cycle of more and more cocaine.
What cocaine does is upset the whole chemical balance in the brain. And the brain, of course, like any organ, tries to adjust to this. But at some point, this adjustment breaks down and psychoses result.
An outcome scientists are struggling to prevent. I'm Randy Atkins for the American Chemical Society. The path to cocaine dependency begins in many places, but always ends at one. And those final steps within the brain imprint dangerous biochemical changes.
We think that these biochemical changes, or some of them, are at the basis of the craving that occurs when you no longer have the drug, or the basis of the crash and the depression that occurs after you've taken the drug.
So scientists are searching intensely for medications to help stop or reverse those biochemical changes. Medications that could make it easier for those now dependent on cocaine to say no.
Appropriate medications can reach people and help hold them in treatment in a way that non-chemical ways may not be able to.
But cocaine is a formidable opponent in this chemical warfare. Its chemical structure acts like a key to one of the brain's most powerful areas, releasing sensations so strong that they overwhelm even the urge for food and water. Animals offered unlimited access to cocaine will ignore food and take cocaine until they die. The lock that cocaine opens is called the cocaine receptor, and determining its chemical structure is one of science's most pressing goals.
Once we had a picture of the lock, then we could start designing keys to inhibit it from being turned, or to design keys that may want to turn it off.
But even a seemingly perfectly designed medication probably couldn't block all the effects of cocaine. The craving, the high, the depression, and success at blocking just one might not be enough.
The cocaine high, for example, block the euphoria so that the patient taking the drug would know, I can't get high. It's unclear that patients would take it. We would have something to offer those who would, though, and that would be very, very helpful. We don't have that right now.
I'm Randy Atkins for the American Chemical Society. Miami scientists investigating a mysterious epidemic of cocaine-related death have uncovered an eye-opening trend. Chemical analyses are revealing more and more bodies with blood levels of cocaine that shouldn't kill, and evidence that an all-too-common practice does.
Before I'd take enough of one drug to overdose on it, I'd add something else to it, change the high up, you know, make it better some other way.
For many cocaine users, that often means easing a painful crash with alcohol.
Some of the unpleasant sensations are somewhat moderated by the alcohol, and the pleasurable sensations perhaps are intensified. And I think we're beginning to understand the mechanism. And I think we're beginning also to recognize the hazardous nature of the chemical reactions that are taking place in their body.
Scientists now know that in the liver, cocaine and alcohol react to form cocaethylene, a rarely studied drug Hearn had seen for years in his chemical analyses of blood. A drug recent animal studies show to be 1.5 times more lethal than cocaine itself. And in humans,
we know that there is a correlation under some circumstances with sudden death.
Biochemical studies also suggest cocaethylene flips the brain's pleasure switches even more efficiently than cocaine, possibly making addiction both more likely and more difficult to break.
Obviously, the dual addiction to cocaine and alcohol is a hard one to break. And if you're going to design an optimal treatment, you're going to need to take into account the actions of cocaethylene.
At the very least, cocaethylene adds another piece to the frustrating puzzle of cocaine abuse. I'm Randy Atkins for the American Chemical Society.